Welcome back. In this video, we look at the neural network algorithm. The idea for an artificial neural network was inspired by biological neural networks in mammals. In the late 1950s, Frank Rosenblatt developed a perceptron for pattern recognition. A perceptron, as we see here, takes inputs, in this case x1 and x2. Each input is multiplied by its own weight, W1 and W2. The weighted inputs go into the perceptron, which is a step function. If the sum of the weighted inputs is above a threshold, the output will be 1, otherwise the output is 0. Rosenblatt built a machine which used potentiometers as mechanical adjustable weights for his perceptron machine. The perceptron was overhyped, and this produced a backlash. Later it was shown that multiple layers of perceptrons with different activation functions were more powerful than the original perceptron design. Here we see a conceptual drawing of a modern neural network called a feed-forward network. The yellow nodes represent inputs. There are 5 inputs here. The cyan node at the far right is the output. Neural networks can have multiple outputs. In between, there are 7 nodes or neurons arranged in 2 layers, 4 in the first hidden layer and 3 in the second hidden layer. Once a network is trained, a new example comes in with its 5 inputs, travels left to right through the network to the output. The output could represent classification or regression. Let's look at a regression example first. I've exported the Boston dataset from R and then read it back in as a CSV file, looking at the first few rows and the dimensions. Next, I'll divide it into train and test sets. We have about 400 in training and 100 or so in test. As a baseline, I'll try linear regression, and we get a mean squared error of 27.4. We'll need to scale the data. Scaling a neural network is not absolutely necessary, but it will definitely converge faster and usually get better results. Here I'm showing 2 different ways to scale the data. This is more or less doing it step by step so you can see what's going on. We're extracting means and standard deviations from only the training data, applying that to both the train and test sets. Rather than doing these steps individually, we can define a scalar using sklearn's preprocessing step and then apply that scalar's transform method to both train and test. I'll go ahead and do it the second way. I'm going to import the multi-layer perceptron regressor. I have a link here in the notebook for the documentation. I'm specifying the network architecture or topology to be 6-3. 6 nodes in the first hidden layer, 3 in the second hidden layer. Let's run that. And you can see there are many other options I could change, and you can always refer to the documentation. Let's make predictions and then evaluate. This got a mean squared error of 29, which was worse than linear regression. So let's try some different settings. 2 most significant changes I'm making here are 1, the solver, which is, in this case, I'm changing to LBFGS. Each of these letters represents someone's name who came up with this approach, which is a quasi-Newton optimization. And I'm increasing the maximum number of iterations, the forward and backward passes, to 1500. And we see that really didn't take that much longer, if at all. And now we got a mean squared error of 15. That is significantly better than the mean squared error of 27 from linear regression, or our first neural network attempt at 29. I did try other network sizes. The more complex the model, the worse the performance I got. And since this is a small data set, a complex network would overfit that and just learn noise in the data. For the classification example, I used the diabetes data set exported from R and read in here as a CSV. I did that so we would have some familiar data to look at. And I'm using the built-in fill-NA function to replace NAs with means for triceps and insulin, dropping the remaining rows that have NAs. It looks like we lost about 44 rows. I need to convert our target, diabetes, to a categorical data type. Now I'm ready to divide into train and test. As a baseline, we'll run logistic regression, make predictions, and we get an 86% accuracy. Again, we want to scale the data. Now we're going to import the MLP classifier, make predictions, and we get a lower accuracy of almost 0.85. Let's drill down into that with the classification report that we can print out. And it looks like it did better on the not diabetes class than the diabetes class. Let's try some different settings. I'm going to try stochastic gradient descent with a simpler model. Our first model had 5 and 2. We'll just make one hidden layer with 3 nodes and bump up our iterations. We got the same accuracy here as logistic regression. With these settings, we weren't able to beat logistic regression, probably for a couple of reasons. One is that this is a relatively small data set, and we did have the NAs, which diluted some of our predictors. The moral of the story here is that neural network is not always better. Sometimes a simpler algorithm will do the job just fine. Both the neural network classifier and regressor and sklearn both use the ReLU activation by default. Other options are identity, which doesn't change anything, logistic or sigmoid, tanh, and ReLU. Sigmoid ranges from 0 to 1 and is the same function we're familiar with from logistic regression. tanh has a similar shape to the sigmoid but ranges from -1 to 1. And the ReLU has been popular for many years. It ranges from 0 to infinity. So any values less than 0 are zeroed out. The ReLU activation function has been popular because it's shown to converge faster. This graph is showing the plot of a neural network I built in R with the neural net function on the same diabetes data. And I'm showing it here just because it gives a nice overview of what the neural network does. So again, notice that each connection from one node to the next in the feed-forward mechanism has its own weight. Also notice that each of the nodes in the hidden layer and the output layer have their own bias or intercept term. In this case, for binary classification, we had 2 outputs for negative and positive. The feed-forward network is basically just matrix multiplication across the network left to right. So how does the learning take place? It's through a method called backpropagation. The first time through a network, weights are randomly assigned, and we'll get a result. That result will be wrong. The error is quantified with the loss function, and the backpropagation step assigns blame to each weight going backwards. In this way, weights are updated on many forward and backward passes called epochs or iterations. Sometimes I visualize this as a bunch of different skiers, one for each node, skiing down different mountain slopes simultaneously, where some slopes are steeper than others. They each have a different gradient. We'll update the previous layer and then the next and the next all the way back to the input layer. Training then is just a series of forward and backward passes until convergence, meaning that the error is under some threshold value. Let's say the same thing in math notation. We need a loss function. Mean squared error can be used for both regression and classification. Our gradients are shown here, not unlike the partial derivatives we looked at earlier in the course, but a matrix of them. And this is how weights are updated. Alpha is the learning rate. If alpha is too small, training will take a long time. If alpha is too large, you might overstep the optimum value. In the sklearn videos, it may have appeared as if I was using a bit of trial and error to find the best architecture or topology network for each problem. In a way I was, but I started out with some rules of thumb. For nodes, the number of nodes or neurons should be between 1 and the number of predictors. One recommendation is 2/3 of the input layer size plus the size of the output layer, and less than twice the input layer size. Recommendation for number of layers is that each layer should have the same or fewer nodes than the previous one. Having more than one layer can capture a more complex relationship between inputs and outputs, but it also may overfit. So for the Boston data set, guideline on the number of nodes, the first guideline here said I should have between 1 and 13. The second one led me to 9, and the third is less than 26. So I chose 9 nodes in 2 layers. And I did try many different architectures. We've seen that there's quite a bit of setup involved for neural networks. We have to define the architecture or topology, the number of nodes that we want in the model, and the number of layers, and also things like the activation function. There's quite a bit of new terminology associated with neural networks. And as usual, I have a quick reference section at the end of the chapter for converting target types for categorical data, scaling the data, as well as how to do either regression or classification. Sometimes people say that a neural network works like a human brain. Let's think about that for a minute, looking back at this diagram with its 7 hidden nodes in 2 layers. It's said that the human brain has about 100 billion neurons, although some experiments have it closer to 85 billion. Either way, all those billions of neurons are connected to 1,000 or more other neurons. Each neuron has multiple inputs that receive signals from other neurons. When the combined inputs reach a threshold, the neuron fires, sending signals out to connected neurons. To say that neural networks, or even deep neural networks, act like the human brain is a gross overreach. We don't fully understand how the brain works. Further, we don't have a massively parallel architecture for artificial neurons on the scale of the human brain. Still, these are very powerful algorithms. In this video, we looked at neural networks. There are 2 reasons that neural networks have received renewed interest in the past decade. One is that processing power has increased, and the second is that we have more data available. In the next video, we look at deeper neural networks. A deep neural network is just a neural network with more hidden layers.